All right, everyone, listen up. With paper one right around the corner, we're going to do a final, super fast revision tour of the whole pure math syllabus. Think of this as the architect's blueprint for success. It's your clear, structured guide to every key concept you need to absolutely nail that exam. So, we've broken it all down into 5 key sections. Now, we're not just listing random topics here. We're grouping them by theme. Why? Because this helps you see the connections, how everything links together, and that is absolutely vital for those big synoptic problem-solving questions. Okay, let's dive right in with Section 1, Logical Foundations. This is the bedrock, right? It's the language and the logic that everything else in maths is built on. In this first part, we're hitting proof, algebra, and functions. Honestly, think of these as the fundamental rules of the game. Get these right, and the rest of the paper just becomes so much easier to handle. So proof. It isn't just about showing you're working, it's about building a completely watertight logical case. You've got your key methods. Deduction. That's your classic step-by-step argument. Then there's exhaustion, where you literally test every single possible case. And of course, disproof by counterexample, where all you need is one case that fails and bam, the statement is proven false. And then you've got this elegant little trick, proof by contradiction. The process is brilliantly simple. You've just got to remember it. First, you assume the exact opposite of what you're trying to prove is true. Second, you just follow the logical steps until you hit something that's impossible, a contradiction. That proves your first assumption was wrong, which means the original statement must have been true all along. Simple. Okay, moving into algebra. This formula, it's completely non-negotiable. You have to know it by heart. But don't forget its hidden superpower, the discriminant. That little b squared minus 4ac part under the square root. It instantly tells you if you've got 2 distinct roots, 1 repeated root, or no real roots at all. That can be a massive shortcut in the exam. Look, your algebraic fluency is critical. Being quick and accurate with surds, your laws of indices, factorizing polynomials, splitting things into partial fractions, and sketching function transformations, that's going to save you so much time and stop you from making silly errors across the entire paper. This is your toolkit. Make sure every single tool is sharp. All right, so now let's see how these abstract rules actually apply to the visual world. In Section 2, we are diving into geometry and space. We're going to explore how we use all those equations to describe shapes and positions. So we'll be looking at coordinate geometry in the classic XY plane. And then vectors, which take us into the third dimension. These are basically the 2 essential languages we use to describe the geometric world. Coordinate geometry is the ultimate bridge between algebra and actual shapes you can see. This is where you'll be using equations of straight lines, figuring out gradients for parallel and perpendicular lines, and using all that to solve geometric problems. And this just brilliantly illustrates the power of it all. As soon as you see an equation in this form, you instantly know the circle's center is at AB, and its radius is R. No messing about. And be ready. You know they love to make you complete the square to get an equation into this nice standard form. Now, vectors. This is where we go beyond the flat 2D page and jump into 3D space. Just remember they have both size, or magnitude, and direction. You've got to be confident with things like position vectors, calculating the magnitude, and using them to solve problems with 3D shapes. Okay, now for some of the most important and versatile functions you're going to come across. These are the heavy hitters, the special functions that are used to model a huge range of real-world stuff. So we're talking about trigonometry. Those are the functions that model repeating patterns and cycles, like waves. And then we have exponentials and logarithms, which are all about modeling really rapid growth and decay. This identity, it is the absolute foundation of trigonometry. Seriously. This and the 2 other versions you can get from it using sec and tan or cosec and cot, this is the key to cracking almost any complex trig proof or equation. You have to master them. You have to remember the fundamental relationship here. Exponentials and logarithms are inverse functions. They undo each other. That's the key to solving any equation where your unknown variable, your x, is stuck up in a power. You just use logs to bring that power down. It's that simple. Let's move on and look at how we handle 2 very different kinds of problems. On one hand, identifying and summing up mathematical patterns, and on the other, finding answers when an exact, neat solution is just impossible to find. So, we're covering sequences and series. That's your arithmetic, your geometric, and of course, the binomial expansion. And then we've got numerical methods, which give us these really powerful techniques for when we just need a good approximation. For any sequence or series question, your first job always is to identify what type it is. Ask yourself, is it arithmetic with a common difference, or is it geometric with a common ratio? You have to know the formulae for the nth term and the sum of n terms for both. It's non-negotiable. And this right here, this is such a cool mind-bending idea that you can add up an infinite number of things and still get a finite, sensible answer. But, and this is the crucial part, remember the condition. The magnitude of that common ratio r has to be less than 1 for the series to actually converge to a number. Look, sometimes you're going to hit an equation that you just can't solve with normal algebra. That's where numerical methods come in to save the day. You'll need to know how to locate a root by showing a change of sign, how to use those iterative formulas to kind of home in on a solution step by step, and of course, how to approximate an area using the trapezium rule. And finally, we arrive at the dynamic heart of pure maths. This isn't about static numbers and shapes anymore. No, this is the mathematics of change, of things in motion. This slide right here probably shows the most important relationship in all of calculus. They are two sides of the same coin. Differentiation is like putting a function under a microscope to find its steepness at one single point, its rate of change. Integration is the reverse. It's about adding up an infinite number of tiny little slices to find the total area under a curve. This inverse relationship is everything. It connects finding maximums and minimums to calculating volumes. If you understand this link, you understand calculus. So after that absolute whirlwind tour, what's the single most important thing you need to focus on? Is it calculus? Is it algebra? What is it? Well, it's not one single topic. The most important skill is seeing the connections. It's using your algebra in a trigonometry problem or using calculus with vectors. The whole exam is synoptic. It's designed to test your ability to pull together ideas from all these different areas to solve one big problem. You've covered the ground, you have the blueprint. Now go in there and show them how it all connects. You've got this.